All right, so here we go. Let's begin with the schedule. All right, so basically we're finishing with 0.7 today, actually. That's not unusual. Okay, so we'll finish up 0.7 on factoring polynomials. We'll do 0.8, 0.9, maybe 0.10. Although if we run out of time, that's okay. All right, the homework on chapter 0 will be due Friday of next week. That's Friday, September 4th of next week, the day after the big homework session on Thursday, September 3rd. All right, so any questions about the schedule? Any questions about the plans? Again, all the videos are on YouTube. Any questions?
Thanks, unfortunately.
Oh, so I'm gonna mute everyone right now at this point. Okay, but feel free to unmute yourself as necessary. Mute all right? But unmute yourself as necessary. Okay, so let's go ahead and start. Feel free to chat, put on your chat. Let's go ahead and start. Let me know if the volume needs to be changed.
Hi, everyone. In section, let's do part D on the test for factorability for quadratic trinomials, QTs. QTs look like this: ax squared plus bx plus c, where a, b, and c are non-zero integer coefficients. So, for example, down here, x squared plus 3x plus 2. That's an example of a QT. It's quadratic because it's second degree, and it's a trinomial because it has 3 terms. We're going to try to factor this old school over the integers, meaning that we're going to decompose this as a product of factors where we're only using integer coefficients. We're not using things like 2/3 or pi. Now, before we apply the test, we need to assume that the GCF is either 1 or -1. If the GCF is 2 or 3 or something like that, you have to factor it out first in order for this test to work. Again, we're trying to see if we can factor something of this form into something like this: a factor times a factor, these 2 linear factors with integer coefficients. Now, we're going to introduce the discriminant, which is b squared minus 4ac. This may sound familiar because this does come from the quadratic formula. It's the radicand under that square root sign. And yes, there is a way to use the QF to help factor these things, these QTs. We'll talk about that in chapter 2. But we're going to use this discriminant to figure out if we can factor a QT like this, old school, into this factor times this factor, something like that. Okay, so let's look at this example. X squared plus 3x plus 2. What are the values of A, B, and C? What are the coefficients? Notice that they're all non-zero and integer. All right? What are A, B, and C? It's good to write these down if you're using the QF, for example. Here, A equals 1, that's the leading coefficient. B equals 3, that's the coefficient on X. And C equals 2. That's the constant term here. Bear in mind, if any of these are negative, make note of that. That's one reason why it's good to write these out or type these out. So let's now work out the discriminant. The discriminant is b squared minus 4ac. So this is going to be, b is 3, and we're going to square that. So 3 squared minus 4, a is 1, c is 2. All right. And if you work this out, 9 minus 8 is 1. The discriminant turns out to be 1. Well, so what? So what? That means that this cutie here can in fact be factored over the integers. This cutie can be factored over the integers, old school, which means that you're not wasting your time with guessing and trying to figure out what these factors are. There's a way to do it. There's a way to break this cutie down into something like this times something like this. Hopefully you don't need this test to figure out quickly that this decomposes as the factor x plus 2 times the factor x plus 1 or vice versa. If you're having trouble with this kind of QT factoring, you may want to practice on Alex. But now, if we had a more complicated QT where the coefficients were more complicated, like a 42 and a 37 and a 111 or something like that, then could we factor that over the integers? Then the test for factorability could be very helpful. By the way, if it is, because the discriminant is 1, why does that mean that we can factor it nicely? Because 1, the discriminant, is a perfect square. It's a perfect square. Perfect squares are squares of integers. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and so forth. So if your discriminant is 0, 1, 4, 9, 16, and so forth, then that means you can factor this QT old school, like so. Something like this. In fact, if the discriminant turns out to be the magical number of 0, then something very interesting happens. If the discriminant is 0, then we have an extra clue as to how to factor this. The QT will factor as a perfect square trinomial. The QT is a perfect square trinomial, and it can be factored as the square of a binomial, meaning that the two factors here are going to be twins. So for example, x squared minus 6x plus 9. If you work out the discriminant, like we did over here, it turns out that the discriminant is 0, which means that if you factor this, you're going to end up with basically x minus 3 times itself, or more concisely, the square of x minus 3. We usually prefer this to this in terms of what we write out. A PST can be factored like so, the square of a binomial. We've seen that before. Now, if the discriminant is not a perfect square, if we get a 2, a 3, a 17, or any negative number, even a -1 or a -4, certainly a -7, then the trinomial is prime over the integers, and we cannot break this down any further. Remember, we're assuming that the GCF was either 1 or -1, all right? And we cannot break this down in a meaningful way, like something like this times this. It's prime. We cannot break this down any further in a meaningful way. The test for factorability, checking to see whether you're wasting your time or not in trying to factor a QT old school, a factor like this times a factor like that. If the discriminant is 0, then that tells you how to factor. It's going to be a PST, the QT is a PST, and it factors as a square of a binomial. We take the x, we grab the middle sign, the minus, we take the square root of the constant term. The square root of 9 is 3, and that's squared. As I said before, I have here 12 factoring examples for you to look at, and I have solutions later on.
Okay, let me just get something in chat here. Any questions before we go on? Any questions before we go on?
Professor, can you replay the last like 40 seconds of this video?
We'll replay the last 40 seconds. Okay.
Yeah. Thank you.
Hi, everyone. And we like something like this times this. It's prime. We cannot break this down any further in a meaningful way.
Over the integers.
The test for factorability, checking to see whether you're wasting your time or not in trying to factor a QT old school, a factor like this times a factor like that. If the discriminant is 0, then that tells you how to factor. It's going to be a PST, the QT is a PST, and it factors as a square of a binomial. We take the x, we grab the middle sign, the minus, we take the square root of the constant term. The square root of 9 is 3, and that's squared. As I said before, I have here 12 factory examples for you to look at and have solutions later on.
Okay, any other questions before we go on? Any other questions? So the discriminant ends up being a number, right? An integer, okay? So if it's like 0, 1, or 4, you can factor nicely, old school, with integer coefficients. If it's like 2 or 3 or any negative number, you're prime, you're dead, you're prime, you're done. I'm assuming that GCF has been taken care of. Any questions before we go on? Chat or vocally, any questions? Okay, feel free to keep chatting.
Hi everyone, let's now go beyond your basic algebra class and let's factor higher degree expressions that are still in quadratic form. And what do we mean by quadratic form? So we're going to factor expressions now that can be expressed as AU squared plus BU plus C after performing what I call a U substitution. We often use the letter U as a substitution letter in calculus. So our expressions can be written like this after performing a U substitution, where, by the way, A is a non-zero coefficient, leading coefficient, and A, B, and C are all real coefficients. So for example, let's factor 2x to the 6th minus x cubed minus 1 over the integers, over z, the set of integers. Meaning I'm going to break this thing down in such a way that all the coefficients will be integer only. So no pi's or 2/3. First of all, let's observe that the GCF is 1. If the GCF is not 1, you have to take care of that. All right. As it stands, we have a trinomial, and it turns out that we can think of it as a QT, a quadratic trinomial, if we perform an appropriate substitution. Well, how do we know that this thing is in quadratic form? Well, take a look at these exponents. The degree here is 6. That's the exponent on the leading term. The exponent on x in the leading term. The exponent here is 3. The exponent on x in the middle term here, by power. Now, let's compare these two powers of x. How is x to the 6th related to x to the 3rd? X to the 6th is the what of x to the 3rd? It's the square of x to the 3rd. Because when you raise a power to a power or exponent, you multiply the exponents. So when you square a power of x like this, you're doubling the exponent. The square of x to the 3rd is x to the 6th. So if you have a QT like this, where the highest exponent on x is twice this other exponent on x, and if you have a constant term over here that's not 0, then this can be thought of as a QT. It's in quadratic form, and it can be written as a QT. If you apply a substitution like this, u equals x to the 3rd, that middle power of x. And once again, if u is x to the 3rd, then what's u squared? U squared is the square of x to the 3rd, or x to the 6th. That's what we did over here. So x to the 6th over here now becomes u squared. I'll erase these. So if x to the 3rd is u, the middle power of x, then x to the 6th is u squared. We can utilize this pattern because, again, the highest exponent is twice that lower exponent. 6 is twice 3. And we have a constant term over here. So when you apply this substitution, u equals x cubed, and also u squared is x to the 6th, then how can we rewrite this in terms of u? We can rewrite this as 2u squared minus u minus 1. We can rewrite this as 2u squared minus u minus 1. And lo and behold, we have a QT. in U. It's a quadratic trinomial in U. You should be able to factor this old school. So we get the factor 2u plus 1 times the factor u minus 1. The factor 2u plus 1 times the factor u minus 1, or vice versa. And then we need to go back to x. So u goes back to x cubed. Again, u goes back to x cubed. We substitute back. And we get the factor 2x cubed plus 1 times the factor x cubed minus 1. Over time, you should be able to go directly from this original trinomial straight to here. You don't have to apply this substitution. This is optional. You don't have to do it. But I think it helps students when they're first starting off with factoring these kinds of 6-degree guys. So I think that these substitutions help, but they're optional. With time, you should be able to go directly and factor the 6-degree trinomial directly as this cubic 3rd-degree factor times this cubic 3rd-degree factor. Okay, question, are we done? Are we done factoring this thing over the integers? It turns out that for the 2x cubed plus 1, the answer is yes. That piece is in fact prime. So the 2x cubed plus 1 does turn out to be prime. We cannot break that further over the integers, and 1 times doesn't count. The 2x cubed plus 1 is prime. We're going to see why in chapter 2. If you don't believe me, I don't blame you, but it does turn out that 2x cubed plus 1 is prime. However, the x cubed minus 1 over here, that's not prime. That's a difference of 2 nice cubes. We have here a difference of 2 nice cubes. And we have a rule for factoring a difference of 2 nice cubes. So we're going to apply the factoring rule. Sorry. We're going to apply a factoring rule for this difference of 2 nice cubes. Basically, factoring a difference of 2 cubes. By the way, if I cover up the 2 here, I'll go ahead and scratch out the 2 here. If we had just x cubed plus 1 over here, we could factor that as well. But the 2 kind of ruins things. We have to give up. That's prime. All right, x cubed minus 1. How do you factor that using the difference of 2 cubes rule? I'll give you 15 seconds to remember it. Remember, it's going to be a binomial times a trinomial, and we're going to use the SOAP trick, the SOAP acronym, to figure out the signs. By the way, the GCF is 1. It helped a lot that the GCF was 1 at the beginning. All right, so let's factor this thing. So x cubed minus 1 factors as x minus 1, which was the more obvious binomial factor, times the trinomial x squared plus x plus 1. How do we get that? X minus 1 was the obvious binomial factor. X is the cube root of x cubed. We use the same sign, the minus sign, just like this over here. The cube root of 1 is 1. And then we build off the binomial factor to get the trinomial factor. So the square of x is x squared. O for opposite sign, that's a plus sign. 1 times x is x. AP for always plus. And then the square of 1 is 1. So we factor this difference of two cubes, x cubed minus 1, as the binomial factor, x minus 1. And then building off that, we get the trinomial factor, x squared plus x plus 1. And don't forget our prime guy over here. But don't forget the factors you already have, the 2x cubed plus 1. All right. At this point, we're done. Remember the trinomial factor here from the difference of two cubes deal? That tends to be prime. Remember, the GCF is 1. If you don't believe me, you can work out the what? That D word. You can work out the discriminant for this QD. Right? The discriminant for this QD turns out to be negative, which means that we cannot factor this further old school over the integers. We have integer coefficients, it's a QD. Discriminant's negative though, so we cannot factor it nicely old school. All right, so there you have it. This 6th-degree polynomial where the GCF was 1, you didn't think you could do this back in your old algebra class. Now you can do it in our pre-calc class. It's in quadratic form. If you wish, do a substitution. You don't have to though. Factor it as a QD in U. Substitute back to powers of x, right? We see that the first factor is prime. In chapter 2, we'll know for sure. X cubed minus 1, we know that we can factor that as a difference of two cubes. It's a binomial times a trinomial. So this guy up here, the 6th-degree thing up here, factors as this times this times this. And at this point, we're done. Okay, next up, we are going to see some more exotic factoring in the next lesson.
Any questions thus far? Okay, after class, well, actually, we'll continue to do examples in these videos. I will do more examples after class if necessary. Okay. But we are timing ourselves. So yes, after class, we can do other examples. Okay, anything right now? Anything right now? And again, as we do more videos, we'll see more. Okay. All right. QD. Okay, what I call a QD is a quadratic trinomial. Okay, spell check. Trinomial. Quadratic means 2nd degree. Trinomial means three terms. So basically, ax squared plus bx plus c, where a, b, and c are non-zero. And real, preferably integer. Any questions? Any questions? And again, I'll do more examples after class as necessary. And in fact,
Hi, everyone.
okay, going like that.
We
okay.
are going to see some more exotic factoring in the next lesson.
You know what? Good time for a video. Okay, I don't want you to fear factoring. Okay, I mean, there are lots of techniques we'll learn. I don't want you to fear factoring. However, this is... Okay, so we're going to factor more exotic expressions now.
Hi, everyone. Let's now factor more exotic, general, rational, and algebraic expressions. Now, really, the principles are old school. And if you ever get confused or disoriented, just think about the old school examples. The basic principles are the same. For example, let's say we want to factor x to the 5th plus x to the 3rd. What do we factor out? We factor out x to the 3rd as our GCF, our greatest common factor. And why is that? Because x to the 3rd is the power of x with the least exponent. The power of x with the least exponent. And that's a theme that we're going to apply throughout this section. To factor out the GCF, we factor out the power of x with the least exponent. So if you look at the exponents here, the 5 and the 3, the least exponent is further to the left on the real number line. 3 over here, 5 over here, 3 is further to the left, so we factor out x to the 3rd. I'm not kidding. We're going to apply these principles later. So we factor out x to the third as our GCF. And when we factor, we do what to get the other factor? We divide. When we factor, we divide. X to the fifth divided by x to the third. X to the fifth divided by x to the third. When we perform that division, what do we do to the exponents when we divide powers of x? We subtract the exponents. X to the fifth divided by x to the third gives us x to the second. 5 minus 3 is 2. Another way to look at it, we start off with 5 as the exponent on x here. We're taking away 3, and the result is 2. When we divide x to the fifth by x to the third, we subtract the exponents to get the x squared. And then when we divide x to the third by itself, we get 1. If you subtract the exponents, you get 0. X to the 0 is 1. So don't forget the old school factoring. It's very instructive. Let's now factor this rational expression over the integers, z. So we only have integer coefficients. Factor x to the negative 7 plus x to the negative 4 minus 2x to the negative 1. What is the GCF here? The GCF here will be the power of x with the least exponent. We have negative 7, negative 4, and negative 1 as our exponents. Which of these three exponents is furthest to the left on the real number line? Which is the least exponent? It's going to be the negative 7. Here's negative 4, here's negative 1, but negative 7 is the least exponent. So we're going to factor out x to the negative 7 as our GCF. Negative 7 is the least exponent on x. Our GCF will be x to the negative 7. Now, when we factor, we do what D word? When we factor, we divide. And when we divide powers of x, what do we do to the exponents? We subtract them. So here's what we do. I'll go to red now. Our GCF is x to the negative 7. So we're going to factor out x to the negative 7. We're going to divide each of these three terms by x to the negative 7 to get the three terms in this other big factor. Again, when we divide powers of x, we subtract the exponents. Now for this first term in here, it's very straightforward. X to the negative 7 divided by itself, well, that's 1. Of course, x cannot be 0, but we won't worry about domain right now. X to the negative 7 divided by itself is 1. Now what about x to the negative 4? What's x to the negative 4 divided by x to the negative 7? When we divide powers of x, we do what with the exponents? We subtract them in this order. Negative 4 minus negative 7. So we get this. X to the negative 4, take away the negative 7 out here. And then for the last term, we have negative 2x to the negative 1. When we divide that by x to the negative 7, we keep the negative 2. When we divide powers of x, we do what with the exponents? Again, we subtract. We have x to the negative 1 minus or take away the negative 7. And then let's clean this thing up. We have the x to the negative 7, our GCF out here. And then for this 3-term factor over here, we copy the 1 plus x to the negative 4 plus 7 minus 2x to the negative 1 plus 7. When you subtract a negative number, you end up adding a positive number. When you subtract -7, you add 7. Then let's simplify the exponents. We have x to the -7. And don't forget the equal sign, by the way. A lot of students forget that. We're writing down equivalent expressions. We have x to the -7 times the quantity, or the factor, 1 plus x to the, well, -4 plus 7 is 3, minus 2x to the -1 plus 7 is 6. So now it's looking pretty clean. We have x to the -7 times the factor, 1 plus x cubed minus 2x to the 6th. But now wait, we don't like to have negative exponents on x in our final answer, usually. So what can we do with the x to the -7? How can we rewrite this whole expression so that we no longer have negative exponents? Well, x to the -7 can be rewritten how? As 1 over x to the 7th. So if you take this big 3-term factor and you multiply by x to the -7, you're basically multiplying by 1 over x to the 7th. When you multiply by 1 over x to the 7th, you're dividing by x to the 7th. So bottom line, the x to the -7 as a factor up here rolls down as x to the +7 as a factor of a denominator. In fact, it is the denominator. This is kind of the jumping rule that we talked about earlier with laws of exponents. So we've come a long way, but we're not quite done yet. It turns out that we can do things with the numerator. Now, first of all, there are actually a couple of things about the numerator that we don't like. And different students can address these issues in different orders. What are 2 things about the numerator that we don't like? Well, aside from the fact it's 6th degree, that's another thing you don't like about it. It's 6th degree. But what are a couple of things we don't like about this guy? The way it's written. All right. A couple of things that we don't like about this guy. All right. First of all, it's not written in descending powers of x. We don't like that. A second thing we don't like is the fact that the leading coefficient, which is what here? The leading coefficient is the -2 here. The leading coefficient is the -2 here. We don't like the fact the leading coefficient is negative. In fact, let's deal with that issue first. Again, students can deal with the descending powers issue first, can reorder the terms, but let's start by dealing with the negative leading coefficient. All right, let's start by factoring out a -1 from the numerator. When we factor a -1 out from the numerator, when we factor, we do what, D-word? We divide. So we factor out a -1, and then we divide each of these 3 terms by -1. When we do that, we basically flip all the signs. We take opposites. So the top becomes -1 times the factor, -1 minus x cubed plus 2x to the 6th. All over the x to the 7th. Now we have basically a -1 factor up here on top. We can pop it out. So we have the opposite of the fraction. Then we have this thing here. -1 minus x cubed plus 2x to the 6th. We no longer need grouping symbols because the fraction bar automatically groups the top and the bottom. Right? So we have the opposite of the fraction, -1. See the opposite sign here comes from this negative sign. All right. So the opposite of the fraction, -1 minus x cubed plus 2x to the 6th. That was the guy in green up here. That's over here. Okay, all that over x to the 7th. Now, as I mentioned earlier, we don't like the fact that the top is still not written in descending powers of x. When we factor, we like to write things in descending powers of x. So let's reorder the terms up there. Descending powers of x. So we have the opposite of. All right. The leading term is now 2x to the 6th up on top. Then we have the opposite of x cubed, or -1x cubed in the middle. We have -1 at the back end. All over x to the 7th. Now, this top guy here may look familiar to you. 2x to the 6th minus x cubed minus 1. We actually factored that thing at the end of section 0.7. I often like to pull this kind of stunt in my notes where I refer to previous examples. So remember, this thing, although it's 6th degree, it is in what form? It is in quadratic form. Because remember, the exponent up here, the 6, is twice the exponent up here, the 3. Right? And we have a constant term up here. So it turns out we can factor this thing as a QD in U, where U is x to the 3rd. Again, that substitution is optional. We factor this at the end of 0.7, right? We started by noticing that the top can factor like so. Again, you didn't need to apply the substitution, but you can. So we get the opposite of the fraction. The top factors for now as the factor 2x cubed plus 1 times the factor x cubed minus 1. You can factor the top directly. I'll do this in green. You can factor the top directly as this factor, 2x cubed plus 1, times this factor, x cubed minus 1. If the substitution here helps factoring this thing as a QD in U, go for it. We've done that before in section 0.7. And all that goes over x to the 7th. Now remember, 2x cubed plus 1, it may not be obvious for now, but it does turn out that that guy is prime over the integers. Notice that 2x cubed is not a nice cube. So we cannot use the rule for the sum of two nice cubes here. We want integer coefficients. But this over here, x cubed minus 1, remember, we can treat that as a difference of two nice cubes. And we have a factoring rule for that. Do you remember how to apply it? I'll give you 10 seconds. All right. So in the end, and we do turn out to be done here, we get the opposite of the fraction, 2x cubed plus 1, that factor, times the factor x minus 1, that's the binomial that comes from x cubed minus 1, times the trinomial factor, x squared plus x plus 1. And we are following the SOAP acronym for the signs. All over x to the 7th. Don't forget that. So this is a nice way of factoring this thing up here. Over here, this in blue shading, that factors as this over here, all of this, with the opposite sign in front. And in fact, you could even make this more compact, because the -1 factor indicated by this opposite sign here, we can multiply it into the x minus 1 over here, and then we can get parentheses 1 minus x. So you could say that the opposite of x minus 1 is 1 minus x. So what you could do is, you could actually eliminate the opposite sign and the x minus 1 factor and replace all that with this factor here, the factor 1 minus x. But you don't have to do that. This is perfectly okay. Next up, how do we deal with fractional and potentially negative fractional exponents? Next.
All right, so there was a lot there. Any questions? Any questions? Why wouldn't the negative be carried onto the leading coefficient? Well, a common question, by the way, is why don't we share the -1 for all three? Now, it's true that the cube of -1 is -1, but I want to point something out here. If you have 2 times the quantity AB, that is not 2A times 2B. So multiplication does not distribute over multiplication. A common question is, why doesn't the factor get shared across all the other factors? Is because of that as an example. I think that addresses Christoph's question. Any other questions? Well, if you multiply by -1, then you incorporate the negative sign, right? So if I say -1 times x minus 1 is 1 minus x, then I zap that -1 out there. So if I'm multiplying in the -1, then I get rid of it. Okay. So yeah, signs can get confusing. But remember, multiplication does not distribute over multiplication. That 2 times AB example is a good example. Although it's true that here, it is true that if you multiply by -1 3 times, the result is that you multiply by -1, because it is true that that -1 times -1 times -1 is -1, but we get kind of lucky there. All right. Questions? Questions? And example 2 could help out also. Let's take a look at that.
Time. Hi, everyone. So let's factor this algebraic expression over the integers, z. Only integer coefficients. Now, the weird thing about this expression is that we have these fractional exponents, the 1/3 here and the -5/3 over here. But again, the same basic principles will apply. Now, first off, a lot of students like to say, oh, can I bring in the 1/3 and just make that an x? Can I share the 1/3 onto these terms? And the answer is a big ol' no. Do not do this. Don't share. I know you're told as little kids to share. Don't share the exponent over sums or differences. You're not allowed to do that. Okay. Exponents, do this in purple. Exponents do not typically distribute over sums or differences. This is related to the idea that the radicals cannot be applied to sums or differences. So basically, exponents and radicals, roots, cannot be applied term by term. So you cannot raise both these terms to the 1/3 exponent. Likewise, you cannot raise both these terms to the -5/3 exponent. I know it's tempting, but know what you can do and what you cannot do. You cannot share the exponent here over sums or differences. Don't apply them term by term. That's true for exponents and for radicals or roots. Now, one thing we can do is use what S word, because of the fact that we have twins here. We have x cubed plus 2 as the common base for these two powers. What technique, what S word might we want to use? In fact, you may be more clever than I am, because when I first typed these notes, I didn't realize I could do this. How about substitution? Substitution. Because when you have twins like this, when you have copies of the same base, then substitution might be a nice technique. So we can replace x cubed plus 2 by, say, u. And I'll do that in my notes. I'll revise my notes. That's one reason it's good to come to class. I revise my notes. All right. Now, first of all, we can do the substitution, and then when we factor, we have u to the 1/3 versus u to the negative 5/3. Now, what do we factor out as our GCF? Remember the old school principles. We're going to factor out the power of u this time with the least exponent. Which is the least exponent? I know it's kind of busy right now, but which is the least exponent? Is it the 1/3 or the negative 5/3? On the real number line, which exponent is least? Which is furthest to the left? It's going to be the negative 5/3. Remember, any negative number is less than any positive number. Negative 5/3 is less than 1/3. Remember, negative 1 million is less than 1. Warning number 5, all negative exponents are less than all positive exponents. I know the negative 5/3 looks more impressive, but it's lesser. It's to the left. It's the least exponent here. So we're going to factor out u to the negative 5/3. So two ideas here. I'm going to apply a substitution. I'm going to substitute x cubed plus 2 with u, and I should state what my substitution is. U equals x cubed plus 2. X cubed plus 2. Not that big. All right, so u equals x cubed plus 2. In fact, I'll throw in the parentheses as well. I'm going to replace all of this with u. So we're going to substitute, and we're going to factor out u to the negative 5/3, the least exponent. All right, 5/3 is the least exponent. That's our GCF. Basically, u to the negative 5/3. All right, so when we factor, we do what D word? We divide. When we divide powers of u here, what do we do with the exponents? When we divide powers of u, we subtract the exponents. All right, so a lot going on here. Again, I'm going to apply a substitution. So it's going to be u to the 1/3. This over here. It's going to be u to the 1/3 plus u to the negative 5/3. All right. Now, which do we factor out? We factor out u to the negative 5/3, the least exponent. So when we do that, we're going to get u to the negative 5/3. All right. When we factor, we do a D word. We divide. When we divide powers of u, what do we do with the exponents? We subtract them. So we start off here with u to the 1/3, right? We start off here with u to the 1/3. I'm factoring out u to the negative 5/3, so I'm dividing this guy here by u to the negative 5/3. So the quotient will be u to the, I start with the 1/3 exponent, and I subtract or take away the negative 5/3. So the 1/3 minus or take away the negative 5/3. That's my new exponent here. You should write it out. The plus sign carries over. Plus sign carries over. And then this guy, u to the negative 5/3, divided by itself is just 1. But don't forget the 1. Put the plus 1 there. All right, so cleaning this up a bit, again, I'll apply my substitution here. So we have u to the negative 5/3 times the quantity, right? It's going to be u to the 1/3 plus 5/3. When you subtract a negative number, when you subtract negative 5/3, you add positive 5/3, right? And then don't forget your plus 1. Over here in the exponent, 1/3 plus 5/3 is 6/3, or 2. So we have now u to the negative 5/3 times the quantity, u squared plus 1. And then at this point, we would substitute back. So then we would get this anyway. We'd be going back to here anyway. So the base, x cubed plus 2, all to the negative 5/3, times the quantity, x cubed plus 2, all squared, and then plus 1. So we'll go ahead and erase the u's now. So we now have this. I'll underline it. We now have that. All right. Now let's look inside here. The square of x cubed plus 2. Folks, can we share the square? To square a binomial, do we just square both terms? I hope your answer is no, absolutely not. You do not do that. You do not share exponents like that. You do not square term by term. Let me repeat, you do not square term by term. Just like you don't apply roots or radicals term by term. You do not apply squares term by term. Remember, what is the square of a plus b? What's the square of a plus b? The square of a plus b is not a squared plus b squared. Sorry, that's wishful thinking. Don't fall into the trap of wishful thinking. The square of a plus b is not just a squared plus b squared. It's not that simple. It is not just a squared plus b squared. It is not just a squared plus b squared. It's not just this. Okay, don't miss the middle term. Don't miss the middle term. It's a squared plus what? Plus 2ab plus b squared. The square of a plus b is not a squared plus b squared. It's a squared plus 2ab plus b squared. Don't forget, for that middle term, you take twice the product of the two terms. Twice the product of the two terms. That's for your middle term here, which a lot of people miss. Don't miss the middle term. Don't miss the middle term, that 2ab term. A lot of people miss it. So then, what is the square of x cubed plus 2? Work it out. Give you 10 seconds. What's the square of x cubed plus 2? Here we go. When you square x cubed plus 2, yes, you square x cubed. And remember, x cubed, all squared. When you raise a power to a power exponent, you multiply the exponent. Twice 3 is 6. So we start with x to the 6th. Right? At the end here, yes, the square of 2 is 4. But don't miss the middle term. Don't miss the middle term. Twice the product of the two terms, the 2ab term. Twice the product of the two terms. We want twice x cubed times 2. We want twice x cubed times 2. Make this nicer. Twice x cubed times 2. That's going to be 4x cubed. 4x cubed. A lot of students miss that. Let's clean this up. 4 plus 1 is 5. We like that math. 4 plus 1 is 5. And what can we do over here? We don't want negative exponents in our final answer. How can we take care of this? Well, we can, again, 4 plus 1 is 5. That's cool. This over here, we can, I'll put this in green. This over here can roll into the denominator as x cubed plus 2 all to the positive 5/3. By the way, in your work up here, you could have rolled this down as u to the 5/3. You could have done that. But eventually, you'll get x cubed plus 2 all to the positive 5/3. And it turns out that here, we are done. So we factored this over here into this. We have integer coefficients. All right. Now, you might be saying, well, wait. On the top, this guy is basically a cutie in u. If you let u be x to the 3rd, this thing is in quadratic form. It's a cutie in U. Can we factor it? Old school. We have here a cutie in U, where U is x to the third. But can we factor this thing nicely? Old school. Well, no, not like old school, as in this times this with integer coefficients. The way I know it, if you write this as u squared plus 4u plus 5, if you do the substitution, you can work out what d word for that. What d word? You can work out the discriminant. Or u squared plus 4u plus 5. You can work out the discriminant for u squared plus 4u plus 5. It turns out the discriminant is going to end up being negative. The discriminant, which is sometimes denoted by this triangle, the discriminant turns out to be negative, so you're dead as far as this kind of factoring goes, over the integers, the old school factoring. Now you might protest, wait, isn't there another way that we could factor this? Aren't there other ways we could do it? That's an excellent question, but it turns out that, well, no, the top is prime over the integers. But good question, right? How do we know it's really prime? That's a great question. Well, it turns out to be prime over the integers. We know it cannot be factored old school like this because of that whole test for factorability. Discriminant is negative. We're dead as far as this goes. So we're done. All right. So next, we're going to attack section 0.9 and we're going to slay what I call monsters next time.
Okay, but before we get to there may be questions. Okay, let me see if I can pull up the notes here. Yeah. So any questions? I'm pulling up the notes here. Wait, we're on 8. Okay, any questions? Let's see. Okay, any questions? All right.
Hi, everyone. Section 0.9 on simplifying algebraic expressions. This is a huge topic. So let's hone our basic tools. A key tool being canceling common factors in a fraction. Very important. Now, some instructors object to the term canceling because students get what my colleague Tony Parsons calls cancel happy. Students often tend to match things up and try to erase them. Be very careful about that. And in fact, a better term than canceling might be dividing or dividing out. When you're canceling, you're really dividing. So what are some principles for canceling or dividing with fractions? As we simplify a fraction, we can cancel a factor of the entire numerator with a factor of the entire denominator, provided that they're non-zero and they're equivalent, like an x and an x. In other words, we can divide the entire numerator and the entire denominator by equivalent non-zero factors. All right. For example, consider this rational expression, x over x squared times the quantity x plus 4. You can see that x is a factor of the numerator, and x is also a factor of the denominator. In particular, it's a factor of x squared. So we can divide the top by x. X divided by x is 1. You have to put the 1 up there. It might even be safe to put parentheses. And then x squared divided by x is x. A lot of students are tempted to just scratch out the exponent. That's micromanaging. That's almost messy in a way. So don't do that. Strike out the entire x squared and put an x below. Again, parentheses are nice to be safe, to indicate that that's a factor of the bottom. And then we can simplify this expression as 1, you need that 1 on top. Don't engage in wishful thinking, folks. You still have a fraction, okay? You have a fraction with a 1 on top now, over, we now have x times the quantity x plus 4. And these two expressions are perfectly equivalent. And notice that both x equals 0 and x equals -4 are illegal, clearly, in both expressions. So we've basically canceled a pair of x factors. We canceled an x factor on top with an x factor on the bottom. We're assuming they're non-zero, and they are equivalent. So this does work out. You can divide out the x factor on top and an x factor on the bottom. Okay, now what if we have something like this? X over x squared plus 4. X over x squared plus 4. Now, a lot of students would do the following. Oh, x goes into x once, x goes into x squared, x times. I get 1 over x plus 4. No, you don't. No, you don't. No, you don't. Why not? Why is that illegal? The problem is that x is not a factor of the entire denominator as it stands. So if you have x over x squared plus 4, we cannot cancel a pair of x factors in the classical sense because x is not a factor of the denominator. Now, if we just had x over x squared, then yeah, x is a factor of the top, x is a factor of the bottom, then you could do a cancellation or division with x's. But the plus 4 down here ruins things. Generally speaking, you want to avoid that kind of top-bottom canceling or division if you have more than one term in the top or the bottom. See, over here, with these guys here, we had factored forms. We had one term, x on top over here, and we had one ugly term on the bottom. It had two factors to it. We had one term on the bottom. There were no primary plus or minus signs. This one in here doesn't count. Over here, we have two terms, two bona fide terms in the bottom, so I do not advise top-bottom canceling or dividing as it stands. All right. Another thing you have to be aware of, hidden restrictions could also arise. For example, if we want to simplify x squared over x times the quantity x plus 4. Well, x is a factor of the top, the numerator. X is a factor of the bottom, the denominator. So here, canceling or division would be appropriate. X squared divided by x is x alone. I'm putting parentheses just to be safe. Over here, when we divide the bottom by x, well, x divided by x here is 1. It's good to indicate the 1 down here. And the x plus 4 still survives. So you end up with x over x plus 4. And that's basically correct, but bear in mind, there is a hidden restriction. I'll put this in red. There is a hidden restriction that you should be aware of when you're dealing with domain issues. Because bear in mind, in the original expression, 0 is an illegal value for x. If you try to plug in 0 for x, you're going to end up with a 0 denominator, which indicates division by 0, and that is illegal. That's not allowed. So 0 is an illegal value for x at the very beginning, and 0 will always be an illegal value for x as we simplify the expression. Now, when we perform a cancellation step, where we completely cancel x factors in the bottom, then we hide that restriction. So in this final expression, x over x plus 4, it's no longer evident that x cannot be 0. So this restriction, x cannot be 0, is hidden. And we really need to write hidden restrictions. Such restrictions must be written out separately, right? Again, when canceling, if a factor, like an x factor, is completely eliminated from the denominator, check to see if any restrictions have been hidden. In this case here, the restriction that x cannot be 0, that's hidden when you completely cancel the x factors in the bottom. So you should indicate that restriction. It's usually acceptable to wait until the very end. You don't have to indicate the restriction as soon as you do the cancellation, but you should indicate it by the end. So now, what I've put in the oval here is now perfectly equivalent to what's in the squish circle here. These are now perfectly equivalent. It's evident that x cannot be -4. That should be evident from both expressions. If you want to write that, that's fine. But the hidden restriction is more imperative to write. All right, next up, fancier ways of dividing or sort of canceling.
All right. Any questions about that, by the way? I know that jazz about the hidden restrictions. Any questions? Any questions? We'll do one more part and then we'll take a break, okay? Any questions? All right.
That's fine. But the hidden restriction is more imperative to write. All right, next up, fancier ways of dividing or sort of canceling. Hi, everyone. Let's now cancel opposite factors. Instead of canceling, what might be a better word? What D word? Dividing. How do we divide opposite factors? Now remember, A minus B and B minus A are opposites of one another, all right? And what do we get when we divide opposites? Non-zero opposites. For example, what is 5 divided by -5? It's -1. Likewise, -5 divided by 5 is also -1. 0 over 0 is garbage, any way you look at it, however. Okay, so the quotient of non-zero opposite factors is -1. Keep that in mind. Classic simplification problem. The fraction 9 minus x squared over x minus 3. And there are a couple of key ways you can do this. First of all, you can look at 9 minus x squared and think immediately, I can factor that as a difference of two nice squares. But how would you do that? Careful. To factor it directly, you would have to factor 9 minus x squared as the factor 3 plus x times the factor 3 minus x. Notice the 3's are in the front. Now, if you write x plus 3 instead of 3 plus x, those are equivalent, so that doesn't matter. But you must write 3 minus x and not x minus 3. So you can factor 9 minus x squared like so, with the 3's in front. Now, what can we do with the 3 minus x up here and the x minus 3 down here? We can divide these factors. How is 3 minus x related to x minus 3? They're opposites. And when you divide opposites, what number do you get? For example, what's 5 divided by -5? Or vice versa. You get -1. So I'll put a -1 up here in parentheses, and I'll put a 1 down here. You should indicate what's left when you divide or cancel out. I'd rather say divide than cancel because when you strike these factors, you do have a -1 remaining, which is really key. So I'd rather say dividing than canceling because importantly, we have a -1 still left up here. The 1 down here is more for form. So 3 minus x divided by its opposite will be -1. A couple of comments. First of all, it's good to put parentheses around the -1 because it reminds us that the -1 is a factor of the numerator and not a term. Because if you don't put parentheses here, some students might mistake the top as the quantity 3 plus x all minus 1. Students might make the mistake of thinking that the -1 is an extra term on the top, and you want to avoid that. So the parentheses help you avoid making that mistake. That's one comment. Another comment is the hidden restriction. When we perform this division, the x minus 3 down here is completely zapped. It's completely divided out, which hides the fact that x cannot be 3. Remember, x equals 3 would be illegal up here because then you'd be dividing by 0. Okay, and that restriction gets hidden in this process. So you should write down the restriction. Again, you can wait until the very end. So then you end up with -1 times all this, or the opposite of 3 plus x, with the hidden restriction that x cannot be 3. If you wish, you can distribute the -1. We get -3 minus x, again, with the hidden restriction. So either of these should be acceptable. Either of these will be equivalent to the given expression way up here. In terms of which may be preferable, that may depend on the context, like if this is part of a bigger problem. So to recap, you can factor 9 minus x squared directly as the factor 3 plus x times the factor 3 minus x. Be careful. A lot of students make this mistake here. When you divide opposites, you get -1. There is a hidden restriction. Make sure you note that. Now, what if you look at 9 minus x squared and you go, wait, I don't feel like factoring that. I'd rather factor x squared minus 9. Well, how is 9 minus x squared related to x squared minus 9? That takes us to solution method number 2, if you don't feel like factoring this directly. Well, 9 minus x squared is the opposite of x squared minus 9. So you can rewrite this as this. That's perfectly okay. You can pop out the -1 factor. The -1 is a factor of the top. You can pop it out. And then you're back to factoring x squared minus 9, old school. So we pop out the -1 factor. X squared minus 9 factors, as you expect, the factor x plus 3 times the factor x minus 3. And then you have a perfect match. The x minus 3 factor up here has a twin, an equivalent factor down there, x minus 3. They divide out to 1. Still, it's good to indicate ones in parentheses on the top and the bottom. And we get the opposite of x plus 3 together with the hidden restriction. 3 is still an illegal value for x down here. If you plug in 3 for x down here, that indicates division by 0, which is illegal. That restriction gets hidden in this division process. So again, we need the hidden restriction. And if we wish, we can distribute in the -1, the opposite of x minus 3, again with the hidden restriction. Notice that these here are equivalent to what we had up in the previous method, up here. Here we basically had -3 minus x with the restriction. Here we have the opposite of x minus 3 with the restriction. Of course, these are equivalent, and they're equivalent to these, which are equivalent. We have 4 equivalent expressions. 4 equivalent expressions, including the various statements of the hidden restriction. Okay, next up, I am not punking you. We're going to simplify this, which you could see in calculus. I'm not kidding. I call these monsters. Not a surprise there. But we'll be able to slay them, and they will no longer be monstrous. That's next time, folks. Get that coffee.
Nice time for a coffee break, don't you think? Let's take a 10-minute break. I think it's 8:19 right now. 8:30 sounds a nice time to restart. Get that coffee. We're going to hit this monster. Take a nice break. All right. Any questions? Let's pause. So again, my notes are under notes for quiz 1A for chapter 0. All right. They're still organized by exam, even though we don't have exams in our term. Any other questions before we start? Any other questions? All right, let us proceed with the monsters.
All right, folks, let's simplify this monster. I don't think I'm offending anyone when I say that. This is a monster. And I'm not joking with you. This is not a joke. You do see expressions like these in calculus. This expression is obtained by applying the quotient rule for differentiation, finding derivatives, to this expression here. A fairly basic algebraic expression. So you do see things like this in calculus, and you may be called upon to simplify these things. I'm not kidding. Now, there are many ways that you can attack this problem, but the key thing is to show work along the way and understand that your friend may come up with a different solution from yourself. All right. So we start here. And we might want to begin by cleaning up the numerator. Because what I have here is what you get when you apply the quotient rule for differentiation directly. Okay, now first off, let's see what we have on the top here in the numerator. How many terms do we have on top? We have one term over here, this times this, and then we have this big second term over here. When you see primary plus or minus signs, that indicates the start of a new term. Of course, there's an implied plus sign out here, right? But we have one term over here, and then this minus sign starts a big second term up here in the numerator. -1 times x squared times 1/3 times this power here times the 4. This is all one big ugly term in the numerator. So we have two terms up on top, which means that we should not be doing any top-bottom sort of canceling or dividing just yet. So for example, many people are going to try to do something with this over here and this over here, these powers of 4x plus 7, but don't divide them out yet. Not yet, because we have two terms on the top. Okay, now let's start by cleaning up the numerator. Now in this first term on top, well, we might want to put the 2x in the front on the left. We often like to put the polynomial pieces on the left. That's not necessary, but visually it might be helpful. For the second term on top, what is the coefficient here? We have a -1 factor. I'll put this in blue. We have a -1 factor. We have a 1/3 factor in here. And we have a 4 factor in here. What is -1 times 1/3 times 4, or 4 over 1? That might be easier for you. When you multiply this together, you get -4 over 3, -4/3. That's the coefficient of the second term in the top, -4/3. Now, do not move any of these pieces over to the first term. That's a very common mistake. Imagine a big river here, okay? Don't cross the river too easily. So don't move the 4 over here, don't move the 1/3 over there. Okay, don't pull stunts like that. All right, so what do we have? Equals, don't forget the equal signs. Okay, we're indicating equivalence. We have the big fraction bar. The denominator stays the same. Okay, so this is no problem. 4x plus 7 all to the 2/3. On the top, the 2x we'll put on the left side. We have the power, 4x plus 7 all to the 1/3. If you're afraid that you're going to confuse the 1/3 as an exponent for 2x, you might actually prefer this. So it's up to you. But I'll put the 2x, the polynomial piece, on the left. That is conventional. And then for the second term in the top, we have the coefficient, the -4/3, and then the polynomial x squared, and then the power, 4x plus 7 to the -2/3. So I'm cleaning up the numerator. I'm making it look nicer. And that's part of the battle right there. And from this point, there are two major strategies that we can pursue. In method 1, we're going to factor the top. We're going to factor the numerator, including these weird powers of 4x plus 7. We've done this kind of thing before in section 0.8. So let's factor the numerator. And we're going to ask ourselves, well, what's the GCF of the top? Okay, so again, let's take a look at the terms here. We have one term over here, and the second term over here in the top. So what can we factor out of both? You could say that we can factor a 2 out of both, although the 4/3 here is a fraction, so that's a little weird, but you could factor a 2 out of both, so that could count as part of a GCF, potentially. All right, x versus x squared. Put this in purple. X versus x squared. Which do we factor out? The power of x with the least exponent, x to the first. We can factor out an x. In green, we can call 4x plus 7 u eventually, do a u substitution. U to the 1/3 versus u to the negative 2/3. Which do we factor out? The power of u with the least exponent, that's going to be u to the negative 2/3. So u, if you do the substitution, or the quantity 4x plus 7, that common base, 4x plus 7, all to the negative 2/3, or u to the negative 2/3. So you could argue that either this or this could be the GCF of the top, the greatest common factor of the top. Actually, the 2 I'll ignore for now. So I'll ignore the 2 issue for now. And as for these guys, actually, it may be difficult to walk and chew gum at the same time. I cannot blame students at all if they wanted to if they wanted to factor out the x first and then factor out this power of u later on, or vice versa. In fact, as it turns out, we may not even have to factor out the x. But we are going to have to factor out this weird power here. Notice the 4x plus 7 here. We have a power of 4x plus 7 in the bottom. I think we're going to have to manipulate this guy. So at the very, very least, I think we're going to have to factor out u, or 4x plus 7, to the negative 2/3 out of the top. Maybe factor out an x also. Maybe factor out a 2 also. But at the very least, we're going to have to factor out this thing. Okay, let's do it. Let's factor the top. Okay, and while we're at it, I'm going to do a u substitution. So 4x plus 7 equals u. 4x plus 7 equals u. I'll type that out. It's good to indicate what the substitution is. Let u equal the quantity 4x plus 7. You should state that. Now in purple here, okay, I apply the substitution. So you're probably going to want to follow this purple column here. Right? So I apply the substitution before I do any factoring. I apply the substitution. We get, well, we get 2x u to the 1/3 minus 4/3 x squared u to the negative 2/3 all over u to the 2/3. So I apply the substitution, and I get this over here. Okay. That required some patience. Don't miswrite things. Often mistranscriptions are the cause of key errors. Just not writing things right. Okay, now, again, you could factor out a 2, but let's not do that right now. Factoring out an x, we may or may not have to do that. Let's go ahead and do that. Let's factor out an x. Let's be ambitious. Let's also factor out the appropriate power of u. Again, we have u to the 1/3 here. We have u to the negative 2/3 here. We would factor out u to the negative 2/3. All right. So here I'm being ambitious. I'm factoring out both the x and the u to the negative 2/3 out of the top. I could not blame you at all if you thought this was too much. It may be too much to walk and chew gum at the same time. So you might want to factor these out bit by bit. As I note previously in my notes, it may be easier to factor out the GCF piece by piece, maybe the x in one step and this power of u in another step. The GCF does not have to be factored out in one step. As it turns out, we may not even have to factor out the x. All right, let's try to factor, and again, we have u to the 2/3 in the bottom, right? So this is good, u to the 2/3 in the bottom. All right, Now on the top, when we factor out the x, when we factor, we do what? D word, we divide. We divide this by x, the x disappears. We divide this term by x, the x squared goes to just a plain old x. So this times what will give me the 2xu to the 1/3 up in the upper left. All right, so who's missing? Who's missing? Who's missing? When we factor out this, what's missing from here that I need to put in here? Well, the 2's missing. 2xu to the 1/3 divided by this, well, 2 divided by 1 is 2. So the 2 I have to put in here. The 2's missing here, so I need the 2 in here. All right, x divided by x, that leaves a 1 in here, times 1. But we don't have to indicate that. X divided by x, there's no x in here. Now, u to the 1/3 divided by u to the negative 2/3. When we factor, we divide. When we divide powers of u, what do we do with the exponents? We subtract them. We started with u to the we started with u to the 1/3. We take away negative 2/3, the exponent out here. So we started with 1/3, we take away negative 2/3. When we divide powers of u, we subtract the exponents. So u to the 1/3 minus negative 2/3. What is that, by the way? And then minus, we carry over the minus sign, right? The 4/3, well, he wasn't out here. I need him in here. 4/3 divided by 1 is 4/3, right? X squared divided by x is x once again. X squared divided by x is x. Again, you could do this in a later step. U to the negative 2/3 divided by itself is 1. So we don't need a u guy out here. In fact, don't put a u power out here. All right, over u to the 2/3. So we factored out x u to the negative 2/3. When we factor, we divide. We see who's left. Okay, after we divide these two terms by this, who's left inside the brackets? All right. What's 1/3 plus 2/3? That's 3/3 or 1, which we don't even have to worry about. U to the first is u. Okay, so we copy this, xu to the negative 2/3. That's not a problem. We copy the 2. Again, u to the 1/3 plus 2/3. That's u to the first. That ends up being plain old u. U to the first is u. And then copy the negative 4/3 x. This all goes over u to the 2/3. So the only thing I did here was that I indicated that 1/3 minus negative 2/3 end up being 1, and we can delete that exponent. If 1's the exponent, we don't need it. Okay, look what we have here. We actually do have one term over one term, which means we can now do top, bottom, canceling, or dividing. We have one term over one term. Remember, one of the key purposes of factoring is to get everything into one term. So over here, we had two terms, but because we factored the top, we now have one term consisting of these three factors. We have one ugly term with three factors: the x, the power of u, and this thing in brackets. So we can now do top, bottom, canceling, or dividing. In particular, I'm looking at the u to the negative 2/3 and the u to the 2/3. U to the negative 2/3 is a factor of the entire numerator. U to the 2/3 is a factor of the entire denominator. It is the entire denominator, so we can now divide. And what do we get when we divide u to the negative 2/3 by u to the 2/3? I'll give you 20 seconds to think about it. Oh, and the answer is not 1. You can't just go bye-bye and the answer is 1. No, no, no. The quotient is not 1. These are not twins. Now, if we had a u to the positive 2/3 up here, yeah, you could just go boom and you get 1 as the quotient of these guys. But no, that's a u to the negative 2/3 up here. These are not twins. So it's not quite that easy. It's not too bad though, all right? So what's happening? We have u to the negative 2/3 divided by u to the positive 2/3. When you divide powers of u, you subtract the exponents. So we get u to the negative 2/3 minus 2/3. What is negative 2/3 minus 2/3? It's negative 4/3. So we have u to the negative 4/3. And if you wish, you could put that in the top and erase the bottom. But what does it mean to multiply something by u to the negative 4/3? Well, how can we write u to the negative 4/3? As the fraction 1 over u to the positive 4/3. Now think of this as being this over 1. This pops down as a factor as u to the positive 4/3. Which means when you multiply by u to the negative 4/3, you're really dividing by u to the positive 4/3. The u to the 4/3 goes in as a factor of the denominator. U was, when you sub back, 4x plus 7. So you end up with 1 over u to the 4/3 as the quotient of these guys, and that subs back to 1 over 4x plus 7 all to the 4/3. All right. We may not be ready, or we could be ready to sub back. Yeah, we could be ready to sub back at this point, actually. All right. So what's happening? All right. I'll erase all this. Although that was the key factor, dividing these powers of u. Key issue. Okay, we have the x here. That goes over here. U to the negative 2/3 divided by u to the 2/3. We end up with u to the 4/3 in the bottom. Okay. Or 4x plus 7 all to the 4/3. Remember, that was our substitution. Remember, u was 4x plus 7. U was the quantity 4x plus 7. So we end up with u to the 4/3 in the bottom, this u guy to the 4/3 in the bottom, right? That's from here. That was all this work here. Inside the brackets, we have the 2. U becomes, I'll do this in green, u becomes the quantity 4x plus 7, do put parentheses, or some grouping symbols. The minus here, 4/3 x minus 4/3 x, that's over here, that's copied. So after you perform this division with the powers of u and you sub back, you end up with this over here. It's like a missile strike. This over here. Can I divide with these guys? No, because the 4x plus 7 is too deeply embedded in there. Okay, we have 2 terms inside the brackets. It's a mess. However, 2 times the quantity 4x plus 7, we can distribute. That's natural, right? So 2 times 4x is 8x, 2 times 7 is 14. Not a problem. So now we're up to here, equals x times the quantity, 8x plus 14 minus 4/3 x, all over 4x plus 7 to the 4/3 exponent. But now, we have another problem. We don't like fractions inside fractions. Now, the 4/3 exponent here may be unavoidable in the end, really, but this minus 4/3 x inside the brackets, we can take care of this. We can take care of this thing so that there's no little 3 in the top. And how can we do that? We can multiply by 1 creatively. So how can we multiply by 1 in such a way that we get rid of the 3 eventually? If we multiply by what over what? How about 3 over 3? Again, we're multiplying by 1. That's always legal. So what we're going to do is we're going to multiply the top and bottom by 3. Compound fractions or complex fractions, that's when you have fractions like these inside a fraction, are typically unacceptable in a simplified expression. Sometimes fractions in an exponent, like 4/3, are acceptable. Okay, so we multiply the numerator and denominator by 3. I indicate that over here, the 3 over here, the 3 over here. That makes this a bit clearer. Okay, and then we can distribute the 3 into here, here, and here. Multiplication distributes over addition and subtraction. Powers or exponents don't, but constant multipliers do. Multipliers do. All right, so 3 times 8x is 24x. 3 times 14 is 42. 3 times this thing, negative 4/3 times x, I'll write that as x over 1, times 3, I'll write that as 3 over 1. Well, those 3 factors divide out, and you get negative 4x left. Basically, the 3 here ends up killing the 3 there. But as it stands, don't just go boom, boom like that, because then you might forget to distribute into here and here. So it's very dangerous to strike these. Okay, do side work. Maybe do this part here as side work. All right, so we have, and also I multiplied the x also. So we have 24x squared, x times x is x squared, plus 3x times 14 is 42x, minus 3x times 4/3 x is going to be 4x squared. So if you wanted to be a bit more ambitious and multiply in the 3x, right? And actually, maybe that's a bad idea, actually. That's one reason why I just multiplied in the 3. In my work here, I multiplied in 3x, but it turns out that you might want to factor out the x anyway. So here, I multiply in 3x, but that might be overkill. But if you multiply in 3x, you get 24x squared plus 3x times 14 is 42x, and then 3x times negative 4/3 x is negative 4x squared. So you have negative 4x squared over here. Over. Now, can we distribute the 3 here through the 4x plus 7? The answer is no. The 4/3 here prevents that. Now, if that were a 1, or if you saw no exponent up there, you could, and you get 12x plus 21 in the bottom. But because you have an exponent here, you're not allowed to distribute easily. Okay, again, do not distribute the 3 in the denominator. The 4/3 exponent forbids that. On the top, we can combine like terms. 24x squared minus 4x squared is 20x squared. We carry over the plus 42x. And it turns out that this will be an acceptable answer. However, we want to make sure that it's simplified. So look, you may want to factor this back to make sure it's simplified, okay? We should factor the numerator back and see if there are any common factors between the numerator and the denominator, besides plus or minus 1. Those are trivial. If you have any non-trivial factors, any common factors besides plus or minus 1, they have to be canceled or divided out. So here on the top, we may want to factor 20x squared plus 42x back anyway. The GCF is 2x. 20x squared divided by 2x is 10x. 42x divided by 2x is 21. Okay, and actually, many books would prefer this form, because then, because the top and the bottom are in factored forms, then you see more clearly that we have a simplified form. It's clearer to see that this is simplified. Now, the expression on the left also turns out to be simplified, but it's not as clear. It's not as clear that this left expression is simplified. Here it's clearer. And also, how do you know when you're simplified? How do we know there's not a 3 factor up here? There's not. If we had a 21x squared up here, we would. But there's no 3 factor up here. We don't get a power of 4x plus 7 up there. If you look at this, you might be able to tell you're simplified, but it helps to factor the top and the bottom to make sure. The bottom's already factored. So again, back here, that's why I multiplied in the 3 to get rid of the 3 of this bottom denominator. But actually multiplying 3x might be too much. You might just want to multiply in the 3 and keep the x out here. Eventually, you can factor out the 2. Again, many roads can lead to Rome. You might do it one way, your friend might do it another way. As long as you show your work, okay, convince a competent colleague. Don't just go, oh, I'm so smart, I did it all in my head, okay? Don't do that. You have to show steps, convince me that you can convince a competent colleague, all right? You have to show things step by step. Although your steps could be different and they could be in a different order. You can adjust your strategy and strategize in different orders. In the end, I would accept either as a final answer, although here on the right, it's clear that this guy's simplified. Wow, that was one way to simplify this big old monster up here. We're going to see a second method in just a moment. We'll start just after we've cleaned up.
So you shouldn't be so afraid of monsters now. Good time for a little video. Don't be a
Second term.
Okay, you know what? Let me go back a little bit to catch the recording, all right?
We have the negative 4/3 over here, remember? And then we can apply the substitution, u equals 4x plus 7, so then we get up to here. All right. Now, in this expression, in method 1, we factored the top. We factored the numerator. Now we're going to try a different method. We're going to rewrite this expression as a compound fraction first. All right. Looky here. We have the negative 2/3 as an exponent on u, which suggests that we can rewrite the second term up here as a fraction. So let's focus on the second term up on top. We get negative 1, or the opposite of the following fraction. We have a fraction here. Now, what are factors on the top and what are factors on the bottom? The 4 up here, I'll put this in green. The 4 up here is a factor on the top, stays on top. The x squared over here, you can think of that as x squared over 1, if that helps. You can think of this as x squared over 1, if that helps. The x squared basically can hop into the numerator. So if you have a factor out here, it can hop into the numerator. Typically not the denominator, though. So the x squared can hop into the numerator. Now, u to the negative 2/3, what is u to the negative 2/3? U to the negative 2/3 can be thought of as what? How can you rewrite that? As 1 over u to the positive 2/3. Which means if you multiply by this, u to the negative 2/3, you're multiplying by the fraction 1 over u to the 2/3. So the end result is that this can roll down into the bottom as u to the positive 2/3. By the way, the 3 down here, the denominator here, is also a factor of the bottom. Now be very careful. These guys in the bottom here, they do not roll all the way down to the bottom here. Do not do that. Do not do that. So the u to the 2/3 here, it goes snugly in here. Do not put it as a twin down below. That would be wrong. That would be wrong. Because then, if you put the u to the 2/3 down here, then it's going to have an impact on this guy over here. You don't want that. All right. So we have a small fraction inside a bigger fraction, right? But again, don't be overly ambitious. What I have in red here is in red here. Do not put the little denominator in as part of the big denominator, the denominator of the big fraction down here. Okay, so now we have a compound or complex fraction. How do we avoid having this in the final answer? Well, I'll put brackets here for emphasis. The fraction bar automatically groups the top together. I'll put the brackets here up for emphasis. What can we multiply the top and the bottom by so that eventually we can kill that bottom denominator, make it a 1? Well, how about this denominator? It's the overall LCD, the least common denominator, 3u to the 2/3. We multiply by that over itself. By the way, we're not worried about domain issues right now. It turned out that negative 7/4 is the only restriction from the domain. And That was true throughout. There were no hidden restrictions. But don't worry about domain right now. We're having a hard enough time with this stuff. All right. So anyway, we're multiplying by 3u to the 2/3 over 3u to the 2/3. Okay, we're multiplying by 1. Again, don't worry about domain right now. And then we use what D word? We can distribute. All right. Now, in this version here, I substitute. In this version, I don't. So let's ignore that part. Let's ignore that part. Okay, we definitely want to look at the substitution version over here. All right. So what I did was I took that fraction I just showed you, okay, this over here, and I'm putting the 3u to the 2/3 factors over to the left. Okay, that might make things easier. All right. So now, okay, let's go ahead and distribute in the top. Do not just go boom, oh, whoops. Don't just go boom, boom, and I get ones. Don't just do that, because then you're going to forget that the 3u to the 2/3 here affects this as well. The left term inside the brackets. All right, so 3u to the 2/3 times 2xu to the 1/3, we get, all right, 3 times 2 is 6. Then we have the x, u to the 2/3 times u to the 1/3. When you multiply powers of u, what do you do to the exponents? You add them. You get 2/3 plus 1/3. What is 2/3 plus 1/3? It's 3/3 or 1, which disappears, right? I mean, u to the first, you don't need the 1. So all this ends up disappearing because it's a 1 in the end. 2xu, right? Minus
6xu.
Now, when you attack this fraction with the 3u to the 2/3, then that's when you knock this denominator out. Okay, let's actually see it. In fact, I'll do this. I'll bring this copy up. Let's actually see it happen. All right. So here I indicate the multiplying, 3u to the 2/3 times 2xu to the 1/3. I just said that you end up with 6xu over here in the upper left, minus 3u to the 2/3 times the fraction. Now, after you've distributed, now you can go strike, strike. And I should put little ones here. But remember, don't do your striking until after you distribute. I better write that out in red. Don't strike or cancel until you distribute first, right? You have to distribute first. Otherwise, you're in danger of forgetting about the fact that the 2xu to the 1/3 also must be multiplied by this. All right, all over, and then the product down there. So now, working on this copy here, as I just said, 3u to the 2/3 times 2xu to the 1/3, that's 6xu. Minus this fraction times its own denominator. Hey, what's 4/7 times 7, or 7 over 1? You get 4. What's 5/8 times 8? You get 5. What's this fraction times its own bottom? You get the top, 4x squared, just like over here. You get the tops. Minus 4x squared over 3 times what? When you multiply powers of u, what do you do to the exponents? You add them. 2/3 plus 2/3 is 4/3 over here. Substitute back. U was, remember, u was the quantity 4x plus 7. Sub back. Distribute. 6x times 4x is 24x squared. 6x times 7 is 42x. Minus the 4x squared over that ugly denominator there. Again, do not distribute the 3 here. That is wrong. Do not. A lot of students want to distribute, and that would be dead wrong. Don't do that. Do not do that. Sad face. Don't do that. Do not distribute because of the 4/3 here. That 4/3 exponent forbids you from distributing that 3 readily. In order for that to work, you have to have a 1 exponent where it disappears. All right, anyway, combining like terms on top, that's okay. 24x squared minus 4x squared is 20x squared, right? And then you have plus the 42x. We aren't done, as it turns out, although in order to be sure that this is simplified, it helps to factor the top. 2x is the GCF on top, and this should look familiar. This is what we got before. Up here in method 1, it's the same thing as what we got before. 2x times the quantity 10x plus 21 all over 3 times the 4/3 power of 4x plus 7. There comes a point where the two methods connect. All right, so once again, what did we do? After we cleaned up and substituted, all right, we rewrote this as a fraction within a fraction because of that negative exponent, but know what's on top, know what's on bottom, and don't roll this little denominator into the denominator of the big fraction. All right, don't do that. That's a common error. Okay, multiply by 1. We multiply by that denominator over itself, but don't strike just yet. You have to do what first? You have to distribute first. That D word, you have to distribute first. You end up with this. Sub back, distribute. That's okay, that's a 1 exponent. Combine like terms, make sure it's simplified, and you're done once again. Monsters. Slay those monsters, and they'll no longer be monstrous.
All right, what do you think, folks? Any questions? Any questions? We've come a long way. Any questions? Okay, you might want to review these videos. So, don't be afraid of monsters. Now, some monsters we still have to be afraid of. All right. No, it's not a spoof. Those were real commercials back in the day. Yeah, that was amazing. I found it on Facebook. All right. Question about the monsters before we go on to some more familiar creatures. Okay, I am recording now, right? Yeah, okay. Let's do it.
Hi, everyone. Let's review rationalizing denominators and also numerators. So when we rationalize the denominator of our fraction, we eliminate radicals and non-integer exponents. Like, for example, the square root of 2 is 2 to the 1/2, right? In the denominator, but possibly introduce them in the numerator. So you may end up with radicals on the top. So for example, in trig, you may know 1 over the square root of 2 as the sine or the cosine of 45 degrees, but this is unacceptable in a simplified expression to have radicals in the denominator if you can rationalize the denominator. So if you have the square root of a non-zero positive integer there, then you should be able to rationalize the denominator. So you take the 1 over root 2, you multiply by 1 creatively, root 2 over root 2, and then you multiply, this is 1, you're multiplying by 1, right? And then you multiply across. 1 times root 2 is root 2 up on top. On the bottom, root 2 times root 2 is root 4, or just 2. Basically, you remove the radical. So 1 over root 2 is equivalent to root 2 over 2. And this is more acceptable as a final answer, like in trig. Now, if you have something like 1 over the square root of pi, or 1 over the square root of x, then we tend not to pull a similar stunt because a pi itself is an irrational number. So there's no point in pulling a similar stunt for this guy. Likewise here, x itself could represent a messed up value, like pi. So we tend not to rationalize or try to rationalize the denominator if we have like 1 over root pi or 1 over root x. But for 1 over root 2 or 1 over root 3, we would tend to rationalize the denominator. Now sometimes we want to rationalize a numerator, where we start off with radicals in the top, and then we want to end up with a fraction where we no longer have radicals in the top, but we might end up with radicals in the bottom. Okay. So for example, later on, when we find the derivative of the square root function, we have to work out this expression, And it turns out that we're going to want to rationalize the numerator. The problem is that if you let h approach 0, then both the top and the bottom are going to approach 0. That's a problem in calculus. So anyway, how do you get an equivalent expression where you rationalize the numerator? All right. Well, how can we get rid of the radicals up there? Students are often tempted to do this, squaring, but you're not allowed to do that. Because if you just have a single expression, you're not allowed to just square it. For example, if I take 3, can I just square it and say that 3 is equal to 9? Well, no, I can't do that. You might be confusing that with solving an equation. There's a difference between re-expressing or simplifying an expression and solving an equation. You're not allowed to square this whole thing just because you feel like it. All right, so what can we do? We can multiply by what magic number? 1, the multiplicative identity. When you multiply by 1, you end up with the original. All right. So here, we're multiplying by 1 creatively in such a way that we're going to remove the radicals on the top. Oh my gosh, so what's going on here? We're using the following multiplication rule. Remember that if we multiply a minus b and a plus b, we end up with a squared minus b squared. If you don't believe me, FOIL this out. Or you might recognize the factoring rule that goes in reverse. This is the factorization of a difference of 2 nice squares, a squared minus b squared. So we want to multiply the quantity root x plus h minus root x by its conjugate. You obtain the conjugate by flipping the sign in the middle. We're taking the copy and we're flipping the sign in the middle. Root x plus h plus root x. And to be fair, we're multiplying on the bottom. That's how we multiply by 1 overall. Now the idea is that when we multiply these two tops together, we're exploiting this rule, something minus some other guy times something plus the other guy. The product is going to be a squared minus b squared. And what are the squares going to do with these radicals? They're going to end up removing them. There are domain issues, like we need the radicands to be non-negative, but let's not even go there right now. So when we multiply a minus b, I'll write these in. When we multiply a minus b and a plus b, we end up with a squared minus b squared. On top, a squared minus b squared. The square of the first guy minus the square of the second guy. The square of the square root of x plus h, which is what? It's just x plus h. Let's put grouping symbols to be safe, although we don't need them in the end. Minus the square of root x, which is x itself. If x is non-negative, but let's not worry about that. Your denominator is ugly. Remember, you have h times all this junk in the bottom. Your denominator is ugly. Even I forget that sometimes. That's wishful thinking to forget this piece down here. So in the top, we have the quantity x plus h. It turns out we can remove the parentheses. They don't help any. Minus the x over here. Over that product. Well, what's x plus h minus x? These cancel. They add up to 0. We end up with h on the top. And when we end up with h on the top, now what can we do? We can cancel or divide out. H is a factor of the top. It is the top. H is a factor of the bottom. We can now do this. H divided by h is 1, top and bottom. By the way, h does not equal 0 is a hidden restriction, but we're not even bothering with domain on this problem. We end up with, don't engage in wishful thinking. We do still have a 1 on top here. We do still have a fraction. We have a 1 that survives on the top. A lot of people forget that. 1 over this piece here, root x plus h plus root x, where h is not 0, the hidden restriction. And yes, these two radicands must also be non-negative, but we won't go there. So notice that with the original over here, we had radicals in the top, but not the bottom. We end up with here, radicals in the bottom, but not the top. But see, in calculus, and in this class, we're going to let h approach 0, and we're going to end up with 1 over 2 root x. Why do we care? That's the derivative of the square root function, given by f of x equals root x. That's in chapter 1. Don't worry about that now. Bottom line, when we rationalize the numerator, we end up with this. The derivative stuff we'll talk about later on. We do prefer this in calculus. In section 0.9, I end with common errors. Common mistakes like root a squared, don't forget the absolute value, things like that. But these are common things, common errors to watch out for. Forgetting absolute value, for example. Also, the idea that the square root of a sum equals the sum of square roots. No, you do not take square roots term by term. Likewise, exponents cannot be shared for a sum or a difference. Be careful when factoring. You share the factor or the radical, basically. Be careful with canceling, right? We cancel equivalent factors of the entire numerator and the entire denominator. We do not take reciprocals term by term. So the reciprocal of the reciprocal of a plus b, that is 1 over a plus b, that's not 1 over a plus 1 over b. That doesn't work. It doesn't split up like that. Over here, remember, a fraction bar implicitly groups its top. So if you have something like this, when you subtract the fractions, don't forget the grouping symbols over here. Because when you subtract the numerators, you're subtracting the group b plus z. Over here, remember that the negative exponent does not apply to the 7. X to the negative 4/3 pops up as x to the 4/3, but the 7 down here, that stays down there as a 1/7. It does not pop up as a 7. The negative exponent does not apply to the 7. We discussed that before in section 0.5. All right, next up, some more gymnastics in section 0.10.
Questions about the rationalizing stuff. Let's go on. Last part.
Hi, everyone. This is section 0.10 on more algebraic manipulations, gymnastics. So, for example, and this is your bread and butter in calculus, you do this all the time. When you want to find the derivative or an integral of something like this, then you want to break it down into a linear combination of powers of x. That is, a number times x to a number plus a number times x to a number. That's called a linear combination. Powers of x. And you want to take the derivative or the integral of this right-hand side term by term. Okay, so let's get an equivalent expression here. Fill in the boxes below with appropriate simplified real numbers so that the left side is equivalent to the right side. All right, well, we have a big old plus sign here, so that does suggest that we have to break up this fraction. And we can do that. We can break up a fraction through the primary plus or minus signs in the top, the numerator. Okay, so when we do that, we get, oh, and before we even go there, the fourth root of x. How do you write that as a power of x? The fourth root of x. That's x to the 1/4. The fourth root of x is x to the 1/4. All right. So you can start by either splitting the fraction or doing this first. Again, the order might not matter. Okay, so here I rewrite the fourth root of x as x to the 1/4, and then I split the fraction through that primary plus sign in the top. We express that as a sum. So I have 7x, or 7x to the first, over x to the 1/4, plus 3 over x to the 1/4. I'm sharing that denominator. I'm reversing the addition of fractions. Okay, Now, over here, when we divide powers of x, what do we do with the exponents? We subtract them. 1 minus 1/4 is 3/4, and we keep the 7 as the coefficient. The x to the 1/4 down here can pop up as x to the negative 1/4. Because that guy down there is a factor of the bottom, it is the bottom, it can pop out or up as x to the negative 1/4. So we're basically done. We have 7 times x to the 3/4, which is 1 minus 1/4, plus 3 times x to the negative 1/4, and we can fill in the blanks. 7x to the 3/4 plus 3x to the negative 1/4. And this is a situation where we do want negative exponents in our final answer. That's the only way we can do this. We do get negative exponents in our final answer, but again, in this form, it's easier to take the derivative or the integral of something like this if you have this kind of format. All right. Now we can split a fraction through the top, but do not split through the bottom. 1 over x plus y is not 1 over x plus 1 over y. In fact, there are no real values for x and y for which that's true, that these are equivalent. So don't split like that. You do not take reciprocals term by term. That doesn't work. So what are some more gymnastics here? Here's an example. Let's say I have x divided by 2/3. If you divide by 2/3, you're multiplying by what? You're multiplying by the reciprocal 3/2. If you don't believe me, multiply top and bottom by 3 over here, and you'll see. But if you divide by a non-zero number, you're multiplying by its reciprocal. But it also works in reverse. If you multiply by a non-zero real number, you're dividing by its reciprocal. And this comes up with equations of ellipses. So if you take x squared and you multiply by 9, or 9 over 1, then you're really taking x squared and dividing by what? The reciprocal, 1/9. Likewise, if you take y squared and multiply by 3/4, that's the same as dividing y squared by what? The reciprocal, 4/3. So this works. When you're multiplying by a non-zero quantity, then you can divide by the reciprocal, and you're doing the same thing. It's the reverse of what you were used to doing. Before, you interpreted a division as a multiplication. Now we're interpreting a multiplication as a division. We're still taking reciprocals. Compensation. How can we express x over x plus 1 as something like this? So here's the idea.
By the way, one comment. If this weirds you out, don't worry too much. It's just something I'm kind of throwing in.
X over x plus 1. How can we write it like this? Well, how do we get a 1 here? We want to make a twin up here. To get a 1, we can construct x plus 1 over x plus 1. So we can make a 1 here by adding 1 to the top. But wait a minute, I can't change a problem because I feel like it. Otherwise, math tests will be easy. How do you pay for adding a 1 on top? By subtracting a 1 also on the top. Now, some of you might have said, oh, wait, can I add 1 on the bottom? Would that work? No, that doesn't work. For example, if you eat 1/2 of a pizza, is that the same thing as eating 2/3 of a pizza? Hey, I'm adding 1 to the top and adding 1 to the bottom. So if I eat 2/3 of a pizza, is that the same as eating half a pizza? That's a great diet, but it doesn't work. That's illegal. You cannot add 1 to the top and the bottom. That's illegal. There's no rule that says that. You can do that. So we don't do this. You pay for adding 1 to the top by subtracting 1 from the top. This is legal because then you're just adding 0 to the top. And then we can break the fraction through at that minus sign. And what happens? We get x plus 1 over x plus 1, which is 1. We get the minus sign. And we get 1 over x plus 1, which is how we fill in the blank. If you didn't get that, don't freak out. But I'm just showing you the kind of things you can do with compensation. If you add 1 to the top, you can subtract 1 from the top. In fact, you better subtract 1 from the top to maintain equivalence. And then you can do some gymnastics. This next one's a bit easier. And this comes up in calculus with integration. Let's say you have a quantity like this. In calculus, you're going to want to multiply it by 4. You'll see why. It's in the technique of integration with U substitutions. Okay, now if you take this and you multiply by 4, how do you compensate for multiplying by 4? Dividing by 4. Or multiplying by what number? Dividing by 4 is the same as multiplying by 1/4. So here we maintain equivalence. This is legal. We're multiplying by 1. If you multiply by 4 and 1/4, you're just multiplying by 1. That's legal. And yes, we pull this stunt in calculus. So here's some algebraic gymnastics that will haunt you throughout calculus. Until then.
All right, folks, that's through 0.10. You can do all the homework through 0.10. That's my stats page. All right, so homework through 0.10. Okay, oh, you're welcome. So thank you. And I know some of you wanted some additional examples. That's fine. Okay, that's it for now. Okay, right now, before I end the recording, anything before I end the recording, you can do the homework through 0.10. Don't procrastinate. Remember, the homework's due at the end of next week. So yeah, get kicking on this stuff. Any questions before I stop the recording? Any questions before I stop the recording? Okay, I'll try to put some Kermit videos up on the playlist. All right, okay, so I'll stop the recording, and let's see if anyone has particular questions. I'll stop the recording.